Hi everyone. This is the machine learning capstone review session, and yeah, I'll be waiting a few more minutes for people to come in. So I'll probably start in another minute or two. And yeah, thanks for the people who have your cameras on. If anyone else wants to turn it on, it's helpful for me to see uh, if you look confused or not.
Good afternoon.
Oh, hello.
Hello, hi.
Hi. Okay. I'm gonna get started now, and there might be more people coming in later. That's okay. So today we're doing the machine learning capstone review, and I understand that the capstone exam is happening soon. So this review session should hopefully give you a better idea of what might be on the exam. And the format really is that I'm going to be kind of giving some explanations of stuff or reviews of materials that you might want to know. Then we'll have a bunch of polls that will have you to answer some questions, kind of like might be on exam or somewhat simplified questions, but they're questions that will help you test your understanding so that you know better what you should be reviewing. And I'll be sending these slides over after the recitations or after this review session. Okay, so remember in machine learning, we had uh, three overall large topics. So the first one is supervised learning, which I'll be spending quite a bit of time on today. And some of the topics that are included in supervised learning are linear classification and regression. So things like linear decision boundaries and uh, margin and so on, and neural networks as well. So unsupervised learning will have clustering and generative models, EM algorithm. So these are things that hopefully you remember seeing. And well, in reinforcement learning, there's just a few topics we didn't talk about too much in class, I think, but there will probably be a question where you have to do some calculations of value iteration and so on. So we'll spend a little time to go over that as well. So for supervised versus unsupervised learning, you should at least at a high level know what are some differences between these types of paradigms. So one of them, you're given labeled data, which is like XY pairs, right? So the idea is that different points now have a label. They can be +1, -1, or their labels can be a real number, and then you want to try to predict them given the x's, right? And then unsupervised data learning, you usually just have an x, right? You just have an x, and then you want to somehow infer some structure about the x's, like if there's a clustering or find a clustering of these x's. That's one example. So the first major topic is linear classification. So remember, linear classification says that, okay, your y's are plus or -1, right? And then you want to try to, each y is associated with the x, which can be a vector. And then you want to find a line that can separate the pluses from the minuses, right? So the setting here is that you have a bunch of pluses, you have a bunch of minuses, and then you kind of want to find a line here that can separate those two. So the form of the line that you'll find is, it looks like this thing, theta dot x plus theta naught equals 0. So what you do when you have linear classification, it says, okay, you try to find out what some good values of theta are, and then you classify by taking the sign of this thing. So what's that mean? It means that if it's greater than or equal to 0, then classify as +1, and if it's less than 0, classify as -1. And if you observe this equation, something that you might notice is that if you flip the signs of this guy, so theta and theta naught, you multiply by -1, then you actually end up having the opposite decision boundary. So you end up predicting uh, each plus as negative and negative as plus. So in this example, like, uh, yeah. So one way to visualize these decision boundaries geometrically is that, okay, you have this form of a line. It looks a little different from the point slope form that you might know, like y equals mx plus b. Um, so how do you visualize this line? Well, here the theta is actually going to be the outward normal direction of the line. So if I look at this picture, so this one is all, it's a line which is all x that satisfy this equation. Uh, theta dot x plus theta naught equals 0. So maybe the outward normal here is theta, right? So theta is always going to be a normal vector to the line. And the points that are classified as positive are the ones that are actually going to be in the same direction as theta. So for this particular value of theta, all the points in this shaded region here are going to be classified as positive, and all the points over here are going to be classified as negative. These are all negative. So you can see that if I flip the direction of theta, if I say like instead of theta dot x, I find negative theta dot x, then it flips the labels because everything that's in the direction of theta from this decision boundary will be classified as positive. So if theta were going to be this way, for example, then everything here on this side would be positive and here would be negative. So let's see. So given that information, so I just told you that theta is going to be normal, it's going to be perpendicular to your separating line or separating plane. I have a poll question for you, which is, okay, I have a bunch of these images, right? And I hope you can see it clearly. One of these is the correct decision rule for theta, and by correct decision rule, it says, okay, the red region should correspond to where you would classify as +1 if you're using theta equals 1, 2, and let's say there's no intercept term, so theta is 0, theta not equals 0. So take a little time to look at this, and you can type your answer into this poll that I have sent in the chat. So maybe if you could finish your answers in like a minute or so. Okay, I think I'll go over the answer to this now. So let's see, the answer is number one. And you can see that because it's theta 1, 2, if you plot it here, like go over there, so this is theta, like this vector, and you can see that it is normal to this hyperplane or to this line. And then you can also see that it's in the correct direction. So the red shaded region should be +1, and the +1 is the things that are classified as +1 are in the direction of theta. So that shows that this is the correct answer. Good. And also, if anyone has any questions, just type in chat or feel free to unmute yourself and ask me. Okay, so remember when I said that if you flip the sign of theta, then you end up with a different decision rule, which flips the labels of your original decision rule. So it turns out that if you have a linear classifier associated with theta, there are actually infinitely many reparameterizations. What I mean by that is that, okay, if I take, let's say I'm not considering an intercept just for simplicity. If I take theta dot x and that's my decision boundary or my decision rule, so then I classify as 1 if it's greater than 0, then if I multiply it by a constant, then it'll give me the same decision boundary, right? So what this means is that there are actually infinitely many decision boundaries or infinitely many theta that give rise to the same decision boundary. So for example, if this is the line given by theta, then for like 1,000 theta, that actually gives you the same line. So if you consider actually theta with only norm 1, so you decide to normalize it, then the decision rule is uniquely parameterized, so meaning that the line that is that gives you the line that gives you the same form of the decision boundary combined with the correct direction is uniquely parameterized. So theta and negative theta give you the same line, but then only one of them will give you the same parameterization of like the same direction of the line. Right, so maybe pictorially, if this is theta and this is 1,000 theta, right? Then so maybe this is theta, then negative theta will be this way. So these two have the same decision boundary, but the decision rule is different. They classify it in the opposite way. So now I have a slightly longer poll, which I'm going to link to you in chat right now. So this is a question that maybe it's the type of question you might see on as a short question on an exam. Maybe, I don't know. Haven't seen the exam yet. So uh, yeah, I'm asking 4 questions here. So there's this diagram down here, and you see that there's red points and there's blue points, right? So the first question says, okay, take the best linear classifier of this form, right? But this form does not include a bias term, so it doesn't include the theta naught term. So what's the best you can do without that theta zero term? The second one says, okay, if I add a theta zero term, what's the best I can do? The third question says that this orange line is a decision boundary that was governed by theta star, right? So this is theta star. And then it classifies everything above the boundary as red. So I'm asking how many ways can you parameterize this decision boundary? And the last question asks, okay, what happens if I flip all the labels of the points? So blue becomes red and red becomes blue. What happens to the error of this classifier? And remember that's error, which is the fraction that's misclassified, not the accuracy, which is the other way around. So I'll give you a few minutes to work on this one as well. So maybe I'll give 2 more minutes to finish this question, or however long you need. I'm still waiting for a few more responses. So. Maybe 30 more seconds to finish up. Okay, I'll go over the answer now. Yeah, so you guys did pretty well on this one. This is a little tricky of a question, so uh, this first question says, what's the error of the best linear classifier of the form sine theta dot x? And the thing that I wanted to trick people on when I wrote this question is, like, you think that there's a line that goes this way, like that's like this would have an error rate of 1/2, right? But the better classifier is one that does this, right? So I should go to the origin and just bad drawing, right? So that this is a better classifier. If you classify this as red and then this as blue, then you end up with an error rate of 1/2 because the red points are correctly classified and the blue points down here are correctly classified. Oh, not 1/2. Did I mention? Did I say 1/2? I meant yeah, 1/3. So here these 2 points are the ones that are misclassified. Well, when you add the intercept term, what this does is that it means that your decision boundary doesn't have to go through this origin point, right? So that means you can have a decision boundary like this orange one, and this one achieves perfect classification. So this is 0. For this third question, so this is a classifier that we said was perfect. It classifies everything above as red and everything below as blue. How many parameterizations? Well, from what I said, there are infinitely many parameterizations. If you rescale both of these by a certain amount, then you get the same decision rule. So, yeah, that's good. And then if you flip the labels of the points, what's the error? Well, the error is going to be 1 because it's, like I said, the blue becomes red, the red becomes blue, and then your classifier gets everything wrong now. Okay, so let's continue. Remember that there is an algorithm to find a linear classifier, which is called the perceptron. I don't have any questions on it right now, so I won't talk about it too much, but you should know the overall outline of the algorithm and what it's for, and what its guarantees are. So basically, it's like a gradient descent thing. So if there's some misclassified data point, you'll do this gradient descent type of update. And then when the data is linearly separable, so you can find a line that separates the two classes, then it's guaranteed to find a perfect classifier in the finite steps, though that classifier is not guaranteed to be max margin in the sense we'll talk about later, and it's not guaranteed to converge to a nice classifier for non-separable data. So yeah, what do we mean by margin? Well, Perceptron says that, okay, if I initialize my data and data not at this purple line or at this orange line, because no data point is misclassified, I'm not going to update. So running, like, if I had an exam question and it says like, okay, initialize Perceptron at this orange line and then run 1,000 iterations of like Perceptron algorithm, then like the answer like there is that, okay, it does not do anything because everything's classified correctly, and Perceptron will not try to wiggle this orange line towards this purple line, even though you might see that this purple line looks like a better fit to the data, right? And kind of a more precise sense, like if you imagine that, let's say like this blue blobs like actually come from a distribution that look like that. These red blobs come from some distribution that look like this. Um, you can see that this orange line will get things wrong if they come from this region, right? While this purple line is more robust. So the purple line is usually what you want in practice, and it's what we say, it's a large margin classifier. Okay, so remember what we said is that training set is for training. Like training set is usually what's depicted on these diagrams here, but then you want to do well on test data, and from what I said before, in this course, we kind of assume that the test data looks sort of like the training data, but you can kind of draw circles around the training data and assume that the test data will be somewhat similar, right? So I have another poll question here for you, which is, okay, for each of these three diagrams, you draw, you have training data, you fit a classifier, and you obtained these lines. So you want to know, okay, which one of these will have high training error or test error, or versus low training error or low test error. And you should make your reasoning given what I said about margin and so on. So I am sending this link. So now this is the poll in the chat. And since this one's a shorter poll, I'll give you probably another 2 minutes to do this. Right, so I think we have mostly everyone. Yeah, let's talk about this one. So, uh, yeah, this first one. So, the training error of this one, well, uh, you can see that this classifies. Well, I forgot to say that you should assume that every, uh, like the um, direction of the decision boundary is like whichever one makes the most sense. So here, this one says, okay, red is like this way, and then blue is this way, right? So this one actually achieves low training error. Like it has zero training error. Uh, it's classified everything correctly, right? The cost here is that maybe at least relative to a different classifier, like if I imagine that there's a blue blob here, right? You're gonna get all of these blue things that lie over here incorrect, right? Because you kind of uh, you uh, compromised your fit in order to accommodate this red point over here. And this red point might just be like an outlier of some sort. Like your data distribution might not like look like that. That's a little weird of a shape. So uh, if you see something like this on the exam, you should say that it's a high test error just because it's like this line is way too close for comfort to this blue uh, region. And similarly, okay, this second one, well, what's the error? It misses this 1 point, but I don't think I would consider that as a high training error, so I would still say it's low. If you only miss a few points, that's kind of okay, right, in terms of training error. And test error, now you're going to be a lot better because you have this blue blob here. Well, you're still classifying everything here correctly. You're still classifying everything here correctly. So this should be low. And then this last one, um, yeah, this last one is kind of all over the place. You can't really do a good linear separator of this. So this will actually have high for both. Okay, that's good. So um, now question is, how do you achieve large margin for a linear classifier? So in order to do that, you need to know what the distance from a point to a plane is, right? well, okay, so we have this point P, and then you have a plane here, which is, say, x transpose theta plus theta naught equals 0, right? And then you want to find what this distance is. And you know that theta goes this way, right? So I'll just show you a quick derivation that maybe gives you some intuition on the margin. So let's say the distance from this point P to this plane, which maybe I'll call it L, this is a line, right? So first let's imagine that we're starting at P. Intuitively, this distance should be how far you have to travel from P to be on the plane, right? Or to be on this line. So you start from P, you travel in this direction, which is the direction of negative theta. How far do you need to travel in order to get onto the plane? So put it mathematically, it says, okay, you start at P, you travel in the direction of theta. So you have to do this normalization here because it's a direction, so it's a unit vector. But how many steps there? Let's say alpha number of steps, where alpha is now going to be your shorthand for what this distance will be, right? So you want this to be on this line. So, well, if you write out what this equation says, it will say that P minus alpha theta over theta naught transpose theta plus theta naught equals 0. So then this will imply, okay, let's do some simplification. Minus alpha square norm of theta divided by theta. Remember, theta transpose theta square norm equals 0. And this implies that alpha, if you do the algebra, would be P transpose theta plus theta naught over norm theta. So let's just say the distance would maybe be a signed version of this, so or unsigned version of this. So let's take the absolute value over norm theta. All right, so this is a distance from a point to a line, and you can kind of just drive it with this cute little derivation where you start from P and then you walk in the direction of theta. Well, now we can actually address what max margin linear classification is, right? So basically we have this decision boundary of theta dot x plus theta naught equals 0. And you can define some sort of margin boundary as being like this. So here is theta dot x plus theta naught equals 1. Here might be theta dot x plus theta naught equals -1. So what's the definition of margin here? It's okay, how far are these decision boundaries, right? So in order to compute how far they are, let's say, okay, let's take a point P on this margin boundary, right? This margin boundary. Then the distance from P to this decision boundary, let's call it L. From before we saw that it's this formula, right? Norm P transpose theta plus theta naught divided by norm theta. But then note that because P is on the margin boundary, what's this absolute value term? It's going to be 1, right? So this is equal to 1 over norm theta. So all in all, this tells you that the width of this slab is 1 or 2 over norm theta, right? Oh, so what does this mean? So basically, when you have points that are over, like we have some sort of points, draw them as like, let's say pluses, and then we have minuses over here. One way of trying to do max marginal linear classification is says, okay, let's try to find the best, oops, the best theta and theta naught, such that everything is classified correctly, but you want to maximize the margin of this classifier. So you want, basically you would want this this line to be as close as possible to this, and then you would want this line over here to be as close as possible to this. And then what we're saying is, okay, we want to maximize the margin of this classifier, and that'll give us like the most separation between the decision boundary to the points. And what I said over here is that, okay, well, actually the margin of this classifier is 2 over norm theta. So this gives you an intuition for why you might want theta to be small. Because max margin classifiers, we saw that like in this previous exercise, that you might want this second classifier and not this first one, right? Because the margin is kind of the distance to the closest data point. And here we saw that's around 2 over norm theta, so you would want theta to be small in order for this thing to be large. And I've just rewritten what I said over here. So one way to do this classification says, okay, make everything classified correctly, pass the margin boundary, and then maximize the width of this slab, so minimize this quantity. So the main takeaway here is that, okay, if I want to have a large margin classifier, I should generally have a small norm of theta. So I want theta to be small in order to have a large margin and thus a more generalizable classifier. And if your data is not linearly separable, in this case, before I had a hard constraint, but now I have a softened constraint. So this would be an objective function that you can use. And you can do some optimization on this. This just says, the first term just says, okay, every term should be classified correctly. But then the second one says, okay, let's regularize. So there's a penalty lambda for having a large norm, right? And then you want to minimize this overall. So now this takes me to another quick pull. I have two fits over here on this diagram, and I'm claiming that they were both generated according to this, like by minimizing this for different values of lambda. So the question is, which one of them would have used a larger value of lambda? And I have sent that poll into the chat. Maybe for the sake of time, let's try to finish this one in like a minute and a half. So just put a quick answer if you can. Maybe 15 seconds if you can put something in. Okay, I think we have everyone. So yeah, I guess seems like we're very a little divided on this one. So um, large margin fit. So first of all, which one of these looks like it has large margin? So in the context of what I said before, you can think of margin as like the distance to to the data, to the closest data point. So this guy over here that looks like it's close to the data, this one's low margin. But this one that's like very far from the data on both sides, this is high margin or large margin, right? So large margin means that small theta, right? That's the argument from the previous slides. And so which one of these has a smaller theta? Well, this this purple line has a smaller theta. And you can kind of see that from this plot already because the slope is for this orange one is kind of large, just intuitively. So this purple one has a smaller theta. And how do you get a smaller theta? Well, in this optimization objective, if you set the lambda is really large, like if you set lambda going to infinity, then this norm theta has to go to 0 in order for this to be finite. So you can think of it as large lambda means small theta, right? So large lambda implies small theta or small norm of theta. So that means that this purple is large lambda. So large margin classifiers, like one of the points here is that if you have theta to be large, or when you have lambda being large, then this gives you a large margin classifier. So yeah, just remember this thing that large lambda, small theta means large margin. Okay, so in interest of time, I will go quickly through some of this last stuff in this linear classification. So nonlinear classification, you can do nonlinear things. The fun thing that you can do is called the kernel trick, but I won't really talk about that. Basically, kernels are things that you can use to get nonlinear fits. That's the idea. You can study it more from the class materials, but basically you have different examples of kernels. So like for one example, if you have pluses and then you have minuses over here, if you use a quadratic kernel, like so, first of all, linear classifiers have to do something like that, right? If you have quadratic, then you can fit something like that. You can fit a parabola of some sorts, right? And I say regularization here works in a similar way, meaning that like this thing is maybe unregularized, or I can even draw like a more dramatic thing. So I can go over here and like make it really close over here. So this is unregularized. So this is maybe like a small lambda type of thing. But then there's a sort of higher margin parabola that you can get. So maybe this is a larger lambda. Right, you can do similar things with cubic, like here, cubic would be maybe you would be able to fit decision boundaries of this form. So if you have data that's like over here, and then over here, like you can't fit this all with a line, but you can fit with cubic. Marta, I see you have a question.
Yes, thank you. I was checking this on the course, and there's an exercise where you have like two parabolas mirrored, like this. And they said this is like a quadratic kernel, and I thought it was an RBF, because how do you get these two boundaries?
That's a good question. So, I think what they mean here is that when you do a quadratic kernel,
You can just have one concave thing. You don't
yeah.
have two.
So you said it was like this, right?
Yeah.
Pluses and pluses, pluses, pluses.
And the minus in the middle.
Yeah, minus in the middle. I think so. If I'm correct on this, I think that it can fit like because of quadratics, you can fit parabolas, but you can also fit like uh, a
To the fourth,
hyperbola.
polynomials to the fourth, but it would be like something like this with three extreme points.
Yeah, I think you might be able to fit hyperbolas with this, though. This might be what the question was asking. So like a hyperbola, like you can kind of fit this type of thing, but nothing
So
more.
hyperbola is quadratic kernel.
Uh, I think you can do that.
Okay,
I might
make
need to
sure
check.
they don't put these questions in the exam, but because it's like a wild guess.
Yeah, maybe I'll think about that more, and
Okay,
I can
thank
send
you.
you an email some other time if I
Thank you.
get a better answer than that. That's a good question, though. Yeah, but yeah, so this RBF kernel radial basis function is just, you can think of it as being able to fit anything that you want. So like pluses and minus. Your RBF can say that, okay, my decision boundary is like this. Like it can kind of fit any crazy wiggly thing that you want. That's for the purposes of this class, that's what RBF is. Any crazy looking decision boundary that looks very squiggly will be RBF. But I will have to check back on that quadratic example. So thanks for pointing that out. Linear regression is a topic. I will not talk about it today, but for the statistics capstone, you do need it. So uh, it's more tested in that one, I would say. So it's a topic, just study it regardless. Hyperparameter tuning is also a topic. You might ask like a conceptual question on it. Basically, it says, okay, how do you find this lambda? Well, in order to find this lambda, what you can do is split your training set into training and validation. So if you have like test, training, instead you can say, okay, this is validation. So if you want to know how good your classifier is for a certain value lambda, like let's say lambda equals 1, then you would train it on this portion. Then you would do testing on this portion to find an error. And then you would treat that as the error for lambda equals 1. Maybe you want to try lambda equals 10 as well. You do the same thing, and then you compare the error rates that you get, and you choose the best lambda. You're not allowed to touch this test set until you're doing the last phase where you actually want to do prediction, because if you pick lambda to optimize the test set, then there's no point in having the test set. Like that's supposed to be held out so you can evaluate how good your estimator is. And cross validation is kind of similar, except that it says, okay, maybe having one validation set is a little expensive. How about let's say, okay, we divide data like this. So maybe shading things might work here. So this shaded region is going to be your test set. Test is shaded, or validation. Your validation set is going to be shaded. And then for each one of these types of partitions, you can treat the rest of it as training and then just this as test, or just this as validation. Then that means for each lambda, like lambda equals 1, you go through each one of these types of partitions, and then you take the average error over all of these partitions. And then you treat that as the error for lambda equals 1. You do the same thing for lambda equals 10, lambda equals 50. You get a bunch of you get like 3 different summaries, and then you pick the lambda that gives you the best one. So these are just procedures that you can try to do to find lambda. If there's ever a question on the exam that says, use the test set to find lambda, that's not the correct answer because you can't use the test set for finding your hyperparameters. Okay, so now we talk about neural networks. So there's probably going to be a question on the exam, maybe 2, I don't know, on neural networks. So you'll need to know different types of neural networks. So we talked about 3 different types in the class, and you'll also probably need to know some backpropagation, or at least the main ideas around backpropagation. So neural networks go through compositions of linear transformations and nonlinear activations. So it's basically a function that's specified by some sort of architecture. So what is this function here? It says, okay, let's say that we have 2 inputs here. So inputs, so this defines a function f of x1, x2. And let's see what we do here. So first we start at x1, this is a node. We say, okay, x1, whenever there's an edge here with a certain weight, we multiply. So we have, like over here, we have x1 transpose w1, right? And over here we have x2 transpose w2. So now I'm labeling this what's called neuron here as 1. The input of this neuron would be the sum of these guys plus a bias term here, which I denoted B1. So I'll call this input to neuron 1. Now, how do you compute an output? Output 1 would be some sort of activation function. So this is what induces nonlinearity, h of in1. Right, so then what we do here is that, okay, well, if I want to compute the input to neuron 2, I would say, okay, that's W3 times the output of neuron 1. So we would say, okay, W or input 2 is equal to W3 times the output of neuron 1 and plus this bias term as well. You can say a similar thing for input 3, which is W4 transpose output 1 plus B3. If you want to, then you can do the same thing for 4 as you do for 1. So what you have here is that the input for 4 is equal to W5 transpose output of 2, which output 2 is still going to be h of input 2, plus W6 transpose out 3 plus the B4. And then your final output for is equal to h of input 4. Right, so if I define this way, then that means this neural network is a function which takes x1 and x2, and it gives you, in this language, output 4. Okay, yeah, let's do this poll. So I have, in this example, I have this, I've set this B1 to equal 1. I've set all these other bias terms to equal 0. And I have all the W's are 1, so it's just kind of a simple thing. And I'm asking you to actually try to calculate what the output is. And I'm saying the activations are x squared. So the activation h here that I described is x squared. So that means that at each of these neurons, you're going to be applying x squared, including the final neuron. So now I'm asking you, okay, if I supply x1 equals -1 and x2 equals -1, then what's the output of the neural network? So I'm going to give you a poll question for this. And let me know if anything's unclear. So I'll give you a few minutes to try to do this calculation. So maybe I'll give 2 more minutes to solve this one. maybe 30 seconds for this one. Okay, I think in the interest of time, I'll go over this one. So basically, we kind of do the same procedure where we need to describe the input and output of each neuron. So let's say what input 1 is. Well, this is going to be x1 times w1 plus b1 plus x2 times w2. Maybe I'll just move this b1 over there just to make it a little closer to what I said before. So that means this is going to be equal to -1 times 1 plus -1 times 1 plus 1, which is equal to -1. Then it says, okay, output 1 is equal to 1 squared, which is equal to 1. Okay, so now I'm just going to write down these inputs to the left of the neurons and then the outputs to the right of the neurons, and I hope it makes sense. So here, the input to neuron 2 is the output of this one times W3 plus the bias term. Well, these bias terms are conveniently 0. So it's going to be 1 times 1, and the output is going to be 1, right? It's going to be the same for this guy. Then what do we do at the end? Well, we take 1 times 1 plus 1 times 1 plus the bias term, which is equal to 0. So I'll write it like more formally. It's 1 times 1 plus 1 times 1 plus the bias term 0 equals 2. So what is this? This is the input to neuron 4. Then what's output of neuron 4 is equal to 2 squared equal to 4. So that's the answer. In an exam setting, we might give you like these definitions of in and out might look different, or they might be defined a little differently from what I have, but we might give you like some sort of definitions for like what is computed over here, what's computed over here, and then we might ask you, okay, well, compute what's at these positions, so compute in 1 or compute out 3 or so on. Okay, so this is how you compute the output of a neural network. How do you do gradient descent? So gradient descent is trying to optimize this network. So you're given a loss, right? Where loss of y and y hat is maybe MSE. So then you will want to find the loss that you incur on this data point, and then you want to minimize this loss. So computing the loss is really the same thing. You just compute y hat, and then you plug it into this MSE equation. So this is what I wrote out last slide. And how do you do gradient descent? Well, you need to do basically the chain rule. So what I mean by chain rule, well, let's try to figure out how to calculate derivatives here. So you ultimately have a loss, which is the loss of y and prediction out 4, right? So let's see what we want to do. So let's say we want to compute the gradient descent update for W5. Right, so the derivative of the loss with respect to W5. Well, one way we can do it is actually compute the derivative of the loss with respect to the output the output at neuron 4 times the derivative output with respect to the input neuron 4 times the derivative of the input 4 with respect to W5. So this is an application of the chain rule, which hopefully you should remember, or if you just go back to your notes on the class, you should be able to pick it up quickly again. In this case, well, since the loss here, let's say y and y hat equals 1/2 y minus y hat squared, the derivative here would just be negative, say negative y minus y hat, but where y hat is evaluated at output 4, right? So if you computed output 4 using that procedure that we talked about to evaluate the neural network, then you can just compute this term. That's easy. Well, how do you compute this guy? It's just the derivative of the h function at the input 4, right? Or let's say h prime. Let's call it h prime of the input. Right, because output 4 is just h of the input. And then this thing here, well, since input 4 is equal to W5 transpose output of 2 plus some other stuff that doesn't depend on W5, that means that this dn over dW5 is just going to equal output 2 because it's a linear thing. So that's going to just equal output 2. So all in all, you would have, if you wanted to compute the gradient with respect to W5, you would get this thing here, negative y minus output 4 times h prime in 4 times output 2. So this is the essence of the chain rule, right? It basically says that, okay, the loss is some function of W5, but like the W5 kind of takes a bunch of steps to get there. Let's break it into these different steps. So how does W5 get to L? Well, it goes through in 4, then that goes through out 4, and then that goes through L. Right? So yeah, in order to compute these, this is a simpler example because there's only like one path in some sense to get from W5 to L. For if you want like B1 to get to L, like you notice that this B1 kind of travels in different paths, right? B1 is mentioned along this path because it's mentioned in the input 2, but it's also mentioned in input 3, right? If you look at the equations for input 2 and input 3. So because B1 here travels through different paths, in order to evaluate the gradient with respect to B1, you need to account for all those paths. So for example, this is one valid decomposition. It says that the derivative of the loss with respect to B1 is decomposing along this path, which is given by this term. So you can do gradient of L with respect to the input of 2 times the derivative of the input with respect to B1. And then same thing for this path. And naturally, these ones you can decompose in the same thing. So like dl over d in 2, well, that's dl over the output 4 times d output 4 over d in 4 times the d in over d out, and like so on. So you can kind of decompose these things, and it's a little annoying to say, but like in exam question, I think on past capstone exams there have been questions that say like, okay, well, which one of these are valid expressions for the gradient, and then you just need to choose the ones that are the correct, have the correct property, account for all the paths basically. And yeah, it doesn't, one thing to know, it doesn't really make sense to say that like, okay, maybe I want to write dl over dw4. Maybe I want to write this dl over dw6 times dw6 over dw4. Well, that doesn't actually make sense, so this is like a no-no. So I'll just like write this, because basically this w4 enters L through something that's not W6. So W4 does not appear in the expression for W6, but appears in L through some other means, right? Which is through the output of 3. So this does not make sense because it actually doesn't count for all those paths. So you need to write valid expressions like this one. And you can kind of see it from the functional form that it should make sense, hopefully. So I have an exercise on these slides, but I think we need to do other things right now. So yeah, I said in the beginning, these slides will be available to you. I'll send them after this recitation, so you can work on your own time.
Questions, please.
Yeah. Yes.
In the previous slide that you were working, this and the previous one, did you know there a typo in the last formula because you number the upper neuron 2 and the lower 3, and the weight is W3 and the bias is B2. These are the weight and the bias of the neuron 2, not neuron 3.
Oh, you mean in this, like in this one?
Yes, in the derivative of neuron 3, the input neuron 3. See?
Input to 3, this is the B1.
Yes, it has weight 4 and
yeah.
bias.
Oh,
and bias.
yeah.
You must
you're
change
right.
You must change the numbers. You must change the numbers of the.
Yeah, you're right. Yeah, so this should be 4 and this should be 3 is what you're saying, right?
Yes.
Yeah. Good catch. Yeah. Thanks. And then a similar thing over here. Yeah. I think that should be correct now. Yeah, thanks for that. So, okay. So different types of neural networks, I'm going to go through this quite fast because I have a lot more to cover. So, convolutional nets, you should remember what they're for, usually for image data, and what they do is fully connected networks have like a bunch of neurons, and a bunch of neurons like here, you have a bunch of connections, and so on. You have too many parameters because basically each one of these guys, each one of these edges now has to have a weight attached to it. So basically if this is D1 dimensional, D2 dimensional, that means they have D1 times D2 parameters. But sometimes you want to incorporate locality in the image, like if you're using image data, like different, there should be some sort of features that are shared among small regions inside that image that you can take advantage of. So that's what convolutional networks do. It basically says, okay, you have an image. Well, what am I going to do? I'm going to take like actually just a small patch of the image, and let's say this is a 3x3 patch. I'm going to have, instead of like doing a lot of weights, I'm just going to have 9 weights here, so 3x3, let's say. Then what I'm going to do is I'm going to slide this image. I'm going to slide this guy over over here. Like, so every time I slide it, I'm going to take a inner product or dot product with the image that's inside that square. So I'm going to take each one of these values inside this square. I'm going to multiply it with the weight with the image value, and then I'm just going to repeat that over and over again. So each one of those gives me a number, and I compile those numbers into a new, like, smaller image. So then that becomes a new sort of feature that you can use. the idea is that when you do this, like even if I do like many different kernels, so this is one 3x3 kernel, if I do like 10 3x3 kernels, well, even if I do that, that's still going to be a lot fewer parameters than this neural network might do. So like, or this fully connected neural network will do. So then I can use all of those features, I can kind of flatten them out into a vector, and then I can do some classification or so on. Right, so yeah, so this is the basics of convolutional networks. And one thing that I think was on, might have been on previous capstone exams was counting the parameters of a convolutional neural network. These I would advise you just like memorize them. It's not like super enlightening, and you don't have to write them down necessarily. I'll give you the slides, but like just put it on your cheat sheet, and it might give you a free point maybe. So yeah, one thing to know is that there are strides. Sometimes it's another feature. You can take this kernel, instead of sliding over by 1, you slide it over by like 10 or something. Not 10, usually 5 or something. 3, 2, 3, 5. So those are convolutional nets. Recurrent neural networks, you hopefully remember something about them. They are used usually for sequential data. A lot of times the examples are text data. And what you should know, like conceptually, are these high-level things here that I've detailed out. And it's basically related to the fact that the recurrent neural network can kind of take variable length sentences, for example, and then encode all of them into vectors. And then you can use those vectors for classification. And the way it does that is it kind of unfolds a neural network so that the neural network like has a number of layers, which depends on the number of words in the sentence, for example. It's a way to do it. So this is just kind of things that you should know. You should review this, but I don't really have time to cover today, so I will keep on going. Okay, neural networks can also overfit, and you can do similar regularization types of things. And you can also use dropout, which is a technique where you just kind of randomly drop edges during the network training. Like you set them out to 0, or you just say that they don't exist. These edges don't exist during training. So you randomly take a few of them and just set them to 0 so that your classification cannot depend too much on an individual weight. That's one way to do it as well. Maybe a conceptual question, not like so much of an emphasis on this though. Okay, so we are finally done with this supervised learning section, which was a lot, I know, but it's also probably a lot of the exam. So let's talk briefly about unsupervised learning. So one thing that you might see is clustering, right? So clustering, remember we're given the task of, we have data now which looks like this, maybe it looks like this, right? And you want to cluster it. So here you want to say maybe that this guy is a cluster, this guy is a cluster, and this guy's a cluster, right? Well, one way to do that is with the k-means algorithm, and the k-means algorithm is an iterative algorithm where you start off with some cluster centers like 1, 2, and 3 at these points. Then you iteratively say, okay, well, let's assign points to the nearest cluster. So maybe these guys get assigned to 2, maybe these guys get assigned to 1, and so on. Then you compute the means of the clusters, and then you set those 1, 2, and 3 to be the means of the clusters. Then you repeat, and you keep on going until it terminates. So in this example, 2 would probably get moved over there, 1 would probably get moved over there, and 3 would probably get moved over there after one iteration. So you can decide how to terminate it, and one important thing about k-means is that it's not necessarily going to terminate at a good clustering because the loss function is kind of messy. It's not really, you don't have nice convexity properties. So that's one thing. K-means is dependent on initialization. So different initializations can give you like kind of drastically different clustering sometimes. Some other problems are saying that, okay, it doesn't automatically scale to non-Euclidean metrics. So like if you want to use something like what's a non-Euclidean metric? I'm blanking. So there are non-Euclidean metrics that you might want to use. You can't automatically use them with k-means sometimes. So it is sometimes a downside. And it's also sensitive to outliers. So if you have a outlying point, then your means might end up shifting to try to accommodate that point, which is not necessarily what you want if you just want to disregard it, right? So one alternative here that we kind of briefly discussed in that course was k-medoids, which says, okay, you do k-means, but instead of allowing your means to be random points in the space, you can allow them, you only require them, let me rephrase this, you require them to be points in the data set. So like these 1 and 2 and 3 cannot be valid means anymore. They have to be points in the data set. And then this turns out to actually be a little more robust to outliers than k-means. So now I have a quick poll for you, which is, okay, I ran k-means for a while. I found that some cluster assignments stopped changing, but I still haven't found a good clustering. So what can I do that could possibly, in some scenarios, produce a better clustering? So you're gonna pick all that apply, and I have sent the poll in the chat. And just for the sake of this last question, let's say that we started off, our initialization is a point in the data. Um, yeah. Okay, I think we have everyone now. So yeah, as you can tell, these first two options are not correct because they won't do anything. Just because I said that you stopped changing your cluster assignment, so you converged. There's nothing else that you can do from that initialization, right? So these last two are both potential options. So I'm going to circle them individually. And why? This third one, new RAM initialization, well, that can't hurt, right? So, yeah, this is what people try and practice. You try from a bunch of different initializations and see if one gives you a good result. And this fourth one, well, I didn't say anything about outliers, but I didn't say that there weren't outliers. Maybe there are outliers, and then maybe something related to outliers is giving you a bad clustering. Maybe K-Medoids is the thing that you should be using instead. So, good. Okay. Yeah, and we're assuming that the initial points were in the data set. So you started initializing at a point in the data set. Yeah. Okay. So yeah, okay. So let's talk about a little bit about generative models. So you can try to fit generative models to data, and the way we fit generative models like a mixture of Gaussians is usually with EM, which is a topic that I'm not going to really cover today, but you should just review it a little bit. When you want to do prediction with like a generative model, then you can like basically learn a model and then cluster new data, right? So these generative models give you a way to actually cluster a new data point. So yeah, so I'll just kind of quickly show you a derivation for what the decision boundary would be when you do this type of model. So let's make this more formal. Let's say, okay, we have a model which is z is equal to -1 or +1 with some certain probability, let's say 1/2 each. And then we have observed data, which is x, and then given what z is, you just treat z as the mean, and then you generate a normal with variance 1. So I have an identity here, but I realize this is a one-dimensional thing anyway, so I'll just say 1. And you want to know what the form of decision boundary is. So how do you find that? Well, let me use a different color. So the decision boundary is where you would be uncertain, right, of the classification. So it says, okay, well, the decision boundary is where I would say 1, or the probability of being 1 is the probability of being -1. Well, according to Bayes' rule, probability of z given x is equal to probability of x given z, probability of z divided by probability x. So for the purposes of comparing these two, like if I do this decomposition, this Bayes rule on both sides, then they have a common denominator, so I don't really have to care about this px. So then this is just saying that at this decision boundary, probably x given z of x, let's say given 1, times the probability that z equals 1 is equal to the probability of x being -1, probability x of -1, or probability z of -1. Right, so how do you find the form of the decision boundary now? Let's say, okay, maybe it's easier to take logs when we do the writing. So if I take logs and I'll expand everything, essentially what I get here is, because this is like e to the -1/2 x minus mu squared, this becomes -1/2 x minus 1 squared time plus log of 1/2 equals -1/2 x plus 1 squared plus log of 1/2. And we can see here that, okay, this is actually going to equal to 1/2 x squared. If we write this out, then it's going to be plus x. Yeah. And then minus 1/2 plus log 1/2 equals -1/2. Sorry, I forgot this negative sign. So -1/2 x squared minus x, and then minus 1/2. plus log 1/2. So you can see here that this term actually cancels out. And then you see that the only dependence on x here is now linear dependence on x. So that implies that actually the decision boundary is linear. Decision boundary is linear. Boundary is linear. So if we asked you to do this in an exam, then you could, in principle, follow these same steps, hopefully, in order to find the form of a decision boundary. And one famous example here is that okay, if these are not identity covariants, like maybe these are different covariances, then you end up getting a quadratic decision boundary. So this is something that hopefully you should be able to derive by yourself. So maybe just do a little review on that as well. And I have a poll here, but I'm not really going to do it. You can think of it about yourself. It says, okay, if instead of being 1/2, 1/2, it was like 1/4, 3/4, what would the decision boundary look like? So you can think about that on your own. These slides here just talk about estimation and the EM algorithm, which you should review, but I don't have time for today because I only have about 12, 15 minutes. So I do want to talk about reinforcement learning since that will probably be a question on the capstone exam. So what are the basics of reinforcement learning that we learned? Well, basically we have states, so that's like maybe where a robot is, like locationally, like where it is on the ground. You have actions, which is like up, down, left, right, what the robot can do. Then you have transitions, which say, okay, well, a robot is now starting at S and it's taking some certain action. So it's saying, okay, well, maybe I'm going to like move my thruster or move my wheel or something and then try to go up. And then S prime is where you actually end up. Sometimes this can be deterministic. So you can say, okay, I try to move up. I always go up. Sometimes it's not. We would specify this in a problem. And then you can have rewards, right? This is your signal for how it's going to inform the robot how it's going to act eventually. Like it needs to learn some way to act in order to get good rewards. So in the fun example of maybe a robot's trying to learn how to fold laundry, it might get a reward every time it correctly folds a piece of clothing, or maybe the reward is proportional to like how messy the fold is or something like that. And then this robot says, okay, well, when I have a certain sequence of actions, I'm going to obtain some sort of reward, and I'm going to discount it so that like maybe rewards that were obtained, that might be obtained like so n steps in the future, maybe they're less important to me than what happens right now. So then the question for a robot now is to say, okay, well, if I'm getting these rewards, then what's the best thing that I can do from any given state, right? And that means, okay, well, at any state, I want to find the action that'll give me the most reward after I take that action. So how do we formalize this mathematically? We say, okay, well, policy is a function that says, okay, for every state, what's the best action? A value function here says, okay, I'm at a given state, then out of all policies, what's the best thing that I can do? Like, and then what's the value that I get from this best policy? So that's value, and the Q function is a related thing that says, okay, well, I start off at a state S, but I also specify an action, right? So after I start off at state S and then do A, what's the best reward that I can achieve? And by properties of MDPs, you end up with these formulas that perhaps should be on your cheat sheets. This first one says, okay, well, the value that I get is just the the reward I get from taking my best action, but that's just Q star of the best action. Right. This second one comes from the Markov property of the MDP. And if you plug this guy into this first one, you get this thing, right? Which is a fixed point equation. So it says that the optimal value function needs to satisfy this. So I might not know what V is or what V star is, but I know that V star should satisfy this equation. So, okay, given these, given what I've said, I have a conceptual poll that I want to give you, which says, okay, I know the value in the Q functions, but I want to find an optimal policy. That was my original goal. So which one of these expressions, or which ones in the plural of these expressions will give me an optimal policy? I'll give you a little bit to do this one. And maybe like 15 seconds for this one. Okay. Yeah, so good. This the correct answers for this one are 3 and 4. So remember the argmax gives you the best argument. So here, this Q star says, okay, well, what's the best thing I can do? Or what's the best value I can achieve by taking an action A starting from state S? Well, that means that the best action should give you the best optimal policy, which it does. So this is true. And then 4 is just a rewriting of this Q star using this sigma, or using this expression. So if we give you value functions and the Q functions, then hopefully you should be able to use this to compute what the actual optimal policy is. And yeah, so it shouldn't matter. If we give you either the Q function or the value function, then you should still be able to compute it using one of these formulas, for example. So with the very little remaining time, I'm going to talk about value iteration. And this is one of those algorithms that you use to compute what the optimal value function should be. So V star is the true optimal value function, right? And we know that satisfies this fixed point relation. So what we can do is that, okay, we start with some old estimate of V star. Then what we can do is say, okay, well, our new estimate of V star of S is based on the old estimate, right? So we kind of repeatedly do this, and then we say, okay, well, hopefully this converges. And once we stop, once this does converge, we actually end up with a V star which should satisfy this, which should be optimal from what we talked about before. So this leads to a value iteration algorithm, which formally says this. Let's initialize what V0 is, and let's just say it's going to be 0 for all S. Then for each iteration until we terminate, like when the value function stops changing, for example, we'll loop through every state, and then we'll say, okay, let's take this old estimate of the value function, and then let's set the new estimate to be this equation, which is based on the old estimate. And this equation says, okay, basically look through every action and then see what the best thing you can do is. And when transitions are deterministic, this simplifies because this sum just becomes a single element. So I'm going to do a very quick example here, just to wrap things up, and I'll leave like a little bit as an exercise for you to try finish off. Basically, what I have here is a grid. There's a good state, there's a bad state, and there are two neutral states, N1 and N2. So we have deterministic transitions, so you can go up or down, left or right. And this value or this reward that you get a reward for leaving a state, right? So whenever you leave the good state, you end up getting 10. Whenever you leave the bad state, you get -10, and then you get 0 otherwise. So now our question is, okay, what's the value function here? So let's say V0, V1, and V2. And the poll on the next slide that you should do on your own time is to compute what V2 is for each of the states. And I'll just compute 1 or 2 just to show you. So we have, let's list these out, right? So you can form a table here. Okay, let's say what's V0 evaluate at G, and so on. So we initialize just by saying everything's 0, right? For, let's say, V1 of G, so this says, okay, well, we need to follow this formula. It says, okay, what's the best action I can take? Well, no matter what action I take from G, I'm always going to get a reward of 10. So if I go to N2, then I get 10 plus gamma, this discount factor, times the reward, or times the value of N2, which is 0, right? And if I go down to B, I get 10 plus the gamma times the value of B in B, which currently is 0, even though intuitively we think that B should be bad, right? So here is going to be 10. For the bad state, it's going to be the same thing. So if I go to the good state, for example, well, at the bad state, I'm going to take a reward of -10. And then what's the value of being at the good state? Well, that's dependent that you, to look at that, you look at this V0, right? And according to this V0, you don't know that the G state is good. So then this actually still becomes -10. So here you haven't actually learned yet that the good state will mitigate this -10. So it's just gonna be like that. N1 and N2 are kind of the same thing. If you do this calculation, then like M1, you can go to B, but according to V0, B does not have any value. Its value is 0. So yeah, basically you haven't, for these guys, you haven't actually really learned yet that the bad states are bad and the good state's good. So this is after one iteration. So after another iteration, let's look at V2. So when you're at the good state, now things are a little more interesting. you have two options. One is to go left and one is to go down. Intuitively, going down is bad, but let's see this mathematically. Now, when you go down, you incur a you give yourself a reward of 10 from leaving the good state, but then you get gamma times the value of being in the bad state, which is -10. So if I went down this way, I would get 10 minus 10 gamma. But if I went this way, I would just get 10 plus, let's say, gamma times 0, which is the value of being in N2, according to the first iteration of value iteration. So obviously I prefer to go left, so I'm going to keep the value at 10. Then once you're at, if you look at this bad state, well, it's kind of similar now. So I could go left and I could go up. Intuitively, going up is better, right? So if I go left, I just get -10 value. But then if I go up, then I get -10 plus gamma times the value of being in state G. So that's, you would reference this value. So that's gamma times 10. So at home, you should go and, I keep on saying at home, I guess you guys are at home. After the session, you should try to figure out what these two values are. If you want more practice, run another value iteration or run another iteration of this. And as long as you can compute a few iterations here and in this format, you should be fine, I think, for the value iteration part of this exam. And the rest of it, there's also Q iteration, but that's kind of the same thing as value iteration. You just do the same thing with the Q functions. So that's all I have for today now. So again, I will be sending these slides out either tonight or sometime tomorrow. And they will have the answers for the questions that I did not cover. Yeah, so good luck on the exam. You guys seem very prepared already, so I'm sure you'll do great. And if you have any questions, ask me, but otherwise, well, I'll let you go.
Thank you. Bye.
Thank you. Bye-bye.
You.
Thank you.
Thank you.